In this lecture, I will explain the print statement used in Python programming. Print statement is used just typing print and supplying an argument for the print command. Here X is the display object. Here we see a simple example. In the Python shell, we have written print hello world. We can try it using the Python shell. If I type print hello world and press the enter key, I see the displayed text here. Hello world is displayed. In general, print command can accept other arguments. One of them is the separator, the other is the AND. Print can be used for files, and we have a flash statement here. Objects are usually texts or strings to be printed. Here we have a separator. Specify how to separate the objects, if there is more than one, of course. The default is the blank space, and is the another argument. It is also optional. Specify what to print at the end. By default, line feed is used /n, and if you want to write strings to file, we provide a file object here. Flash is not very frequently used. It is a Boolean expression specifying if the output is flashed or buffered. If the flash argument is set to true, the print function will not buffer the data to increase the efficiency and will keep flashing it on each call. So this flash is used to increase the speed of the print command. If true is written here, then print function works faster. Okay, let's see other examples. In this example, as you see, we use two words separated by comma, and if we execute this command, we see that hello world is displayed. Let's try this command on the left hand side. Okay, I pasted print hello comma world. Okay, the display is the same as in the previous one. I mean, both words are displayed, and a space between these two words is available. Okay, let's see another example. Here the optional argument separator is used. This is our first string to be displayed. This is the second string to be displayed, and these two strings are separated by these 3 dashes. Okay, let's try it. I copy and paste it on the left hand side and press the enter key. So as you see, these two strings are concatenated, and in between the separator string, now it is a string consisting of 3 dashes, and it is used between these two strings. This is another example. For the separator, we wrote none, but even so, a blank is available, a space is available between these two strings. As you see, we use single quotation marks for the strings. In our previous example, we used double quotation mark. I mean, there is no difference whether you use single quotation mark for the strings or double quotation marks. Okay, next example. In this case, we put a space between single quotation marks, and this is our separator. If we run this program, we see that a similar print is seen. There is a space here between single quotation marks. Okay, see another example here. In this case, we don't have any space between single quotation marks here. There is no space here. If we try this command, we see that the strings are concatenated. There is no space between these two strings, and also there is no space also between these two single quotation marks. Okay, see the next example. In this example, for the separator, we use line feed /n. We see that the first string is displayed, then we go to the next line and second string is displayed. So let's try it. As you see here, first string is displayed and separator is /n, then next string is displayed. Okay, this is another example. Here we use just a slash to separate the strings. So as you see, strings are concatenated, and between them slash is used. Slashes are used. So let's try this example also. Okay, as you see here, strings are concatenated, and between two string slash is used. It is given here. Now I will consider the string format used in print statement. Here we define a variable price, and this is the value of the variable, and this is a string indicated by txt. We have curly braces here. Okay, and we use the print statement txt format price. For the place of the curly brace here, this value is inserted, and this is achieved using this format. Okay, let's consider this example. Let me copy it, and now I will use a file. I can create a file here using the new file. I already did it, so I'm just copying the Python statements here and run the program. So what do we see? Print statement prints the price is, and here for the place of the curly brace, the value here is printed, and the rest of the sentence comes. Okay, now see another example illustrating the use of the format for the print statement. Here we have two variables. One of them is the age, and the value is 36. This is another variable. Value is a string here, and we have another string here. His name, and curly braces, we have a number here, and dot, curly braces 1 is curly braces 0 years old. So, and this text is printed using the print command, and of course format is used here. As you see, the arguments are age and name, and the index of age is 0, index of name is 1. So his name is, and for the place of 1, what is written? Name is written, George. George is written here. Then George is 0. 0 indicates the age, and that's value 36 is printed here, years old. So when we execute this command, what we see? His name is George. George is 36 years old. Okay, let's try this. I copy it and paste it here. Okay, I run it using the F5, or choose here run module F5. I can use the shortcut F5. If I press to the run, choose F5, and we see that his name is George. His name is argument 1 is the name here, that is George, and George is argument 0, 36 years old. George is 36 years old. Another example illustrating the use of the format in print statement. Now we see we have 3 variables. They all hold integers, and here I have a string. I want curly brace, pieces of item number, another curly brace for, and we have a column dot 2f, then dollars come. Then we use print statement like this. My order, this is the string, format, quantity. So the string is printed for the first place of curly braces. Quantity is printed. Then pieces of number, item no, for the place of the second curly brace, item no is printed. And then for the place of the third curly brace, price is printed. That 2f means use 2 digits after fraction. So let's try this. I'm copying it and pasting it to my window. Okay, let me run it. I will use shortcut F5. Okay, so what do we see here? Okay, I want 12 pieces of item number 456 for $123.00. Since this is an integer, after that 2 digits will be used, and for the places of 2 digits, zeros are used. In this lecture, I will explain the numbers which are data types used in Python programming. One of the data types used in Python programming is the numbers. Okay, we see here classical addition operation performed on integers, so we can sum the integers directly using Python. Here we have a floating point number. This can be considered as a fractional number. It is multiplied by an integer. The result here is nothing but a real number or fractional number or floating point number. So if you multiply a floating point number by an integer, the result is an floating point number. Here 2, we have a double star here and 100. This means 2 to the power 100. And Python can easily compute such large numbers. So let's make practice on the idle shell of the Python. 123 plus 222 equals 345. 1.5 multiplied by 4. So multiplication of a floating point number by integer is a floating point number. And 2 to the power 100 can also be easily calculated. I'm sorry, I should use 2 star. 2 to the power 100 equals to this number. Okay, 2 star means power, 1 star is multiplication. Okay, Python can calculate very long numbers. Here, this is 2 to the power 1 million. We have 6 zeros here. Even Python can calculate this number. When this number is calculated, we get a very large integer, and the number of digits in this integer can be calculated with this command. What do we do here? We first convert the calculated number to string. Then, using the len function, we calculate the number of characters inside the string. Each character here is a digit. So, as you see, the result will be at almost 300,000. Okay, there are 300,000 digits inside this large number. So let's try it. Okay, let me copy and paste to save time. As you see, it took some time to calculate this number, and we convert this number to string, then calculate the characters inside this string. Each character is nothing but an integer. Okay, we can use a short value here to see the evaluation. Okay, I am omitting the len here. Okay, 2 to the power 10 is a number that is equal to 1024. Then we convert it to a string, and inside the string we have 4 characters. Okay, so if I type len in front of this expression, I get 4. Okay, let's continue with the other expressions on the PDF. Here, this is math module. We will see the modules in other lectures. To use some specific numbers like pi, e, we have to include this module using the import command. Otherwise, we cannot use pi directly. For instance, if I type matpy, as you see, an error appears. So we include the math module. Then we can type matpy. Pi value will be displayed. And also there are other built-in functions available in this module. One of them is the square root. We can calculate the square root of 85 using math.sqrt 85. Okay, I'm just copying and pasting. Let's proceed with the next page. Here also we consider classical addition operation. An integer is added to a floating point number. The result is a floating point number. We can truncate fractional numbers by casting. Here, integer casting is used. We have a fractional number, what happens? The digits after dot are removed. Of course, dot is also removed. We only take its integer part, that is 3. We can do the reverse also. An integer can be converted to a floating point number. This is an integer. If we convert it to a floating point number, a dot and a 0 is added. So let's try this. Okay, let me first consider truncation. As you see, the fractional number is truncated and integer is obtained. And we can convert an integer to a fractional number using casting also. Here, float is used to cast integer 3 and convert it to real number 3 or floating point number 3.0. Okay. Now I define two variables here, a and b, a equated to 3, b equated to 4, and we can perform arithmetic operations easily. A plus 1 is addition of 3 to 1, a is 3, a minus 1 is the subtraction that corresponds to 3 minus 1, and the result is, as you can easily guess, 4, 2. Whatever we write after this arrow on the right hand side, separated by commas, are displayed. I mean, the result of these operations are displayed as a table. This is a table. We will consider table data type in other lectures. Okay, here b is multiplied by 3. B is an integer, 3 is an integer, so the result is an integer, that is 12. And b divided by 2, b is an integer, this is division, classical division operator, but the result is floating point number. Okay, let's consider these operations. A equals 3, b equals 4, a plus 1, a minus 1. So as you see, I only see a single digit. If I type a plus 1, comma, a minus 1, I see the results as a table. And b is multiplied by 3, the result is an integer. When b is divided by 2, the result is a floating point number. Okay, let me continue. Again, we are considering the same integers, a equals 3, b equals 4, and this is remainder modulus operation. We divide a by 2 and take the remainder. A equals 3. When 3 is divided by 2, what's the remainder? That is 1. And here b is integer 4, and we take the second power of b, that is 16. So the result will be 1, 16. And 2 is added to 4. The result is a floating point number. Here we have a floating point number, and b is an integer, that is 4. The result is floating point numbers, 16. Look at here. The result of this operation is an integer, 16. The values are the same, but types are different. Here the result is also 16, but the type of this number is float. Here it is integer. And here we perform division and addition operations. b is equal to 4, it is the integer, divided by 2.0 plus a. So the summation result here is 5. But what is that? That is a floating point number. So the division of 4 by 5 is a floating point number, and this can be written 10 divided by 8 divided by 10.0, that is 0.8. And this 0.8 can be displayed using scientific notation here. This is format, display format, and this is the number to be displayed. Percent E means use the scientific notation, and this is nothing but 0.8. This E means 10 multiplied by 10 to the power. Power term is indicated here. That is minus 1. 1 means 1. And this is nothing but 0.8. Okay, proceed more. But before proceeding more, let's try some of these. For instance, this is new to us. We can try it. A percent 2, the result is 1. If I type a percent 3, the result will be 0. Okay, let me also try this one. Number equals b divided by 2 plus a, and then what I do, I display the result using scientific notation. Okay, the result is 0.8 displayed in scientific notation. Okay, let's see the other slide. Here number is a fractional number. This is integer. This is floating point number. So the number is a floating point number. We can display the number typing num directly, or we can display the number using the print command. They give the same output. Here we see how to detect the type of the numbers. For this purpose we use the type command. A is an integer. If we write type A, class int will be displayed. So let's try this. So we define A equals 1, then we write type A. So we see the data type. And similarly for the others, B is equated to 1.0. This is floating point number. If we write type B, class float will be displayed. Here we have a string. This is not a number, it is a string. If we write type C, class string will be displayed. Here we have complex number 1 plus 3j. If we write type D, type class complex will be displayed. Okay, let's try it. If I type D equals 1 plus 3j, complex numbers are constructed using j, not I. I is not used in Python. Be careful. I and j both are used in MATLAB, but here in Python only j is used to describe the complex numbers. And if I write type D, I obtain the type of the number that is complex here. So integer precision about the calculated numbers. Python 3x supports unlimited size for the number calculations, integer number calculations. This is a huge number, 1 is added, another huge number is obtained. This is 2 to the power 200. This large number is even calculated using Python. As you see, I type 2 to the power 200 and a very large number is easily calculated in Python. I already said complex numbers can be obtained using the J symbol. Here two complex number 1j multiplied by 1 capital J. Capital J is also accepted as complex value. So 1j is multiplied by 1 capital J. The result is minus 1. That is j square. Here we can try other examples. 2 plus 1j multiplied by 3, that is 2 plus 3j. And let me try this example also. 2 plus 1j multiplied by 3, the result is 6 plus 3j. In this lecture, I will continue on explaining the numbers used in Python programming. I will explain hexadecimal, octal, and binary number definitions in Python, and I will also provide some functions available in math module. Binary, hexadecimal, and octal numbers can be defined in Python. For octal numbers, we first put a 0, then letter O, then digits between 0 and 7 can be placed. Here we see some examples. This is 0. Don't confuse it with the letter O. Okay, this is letter O. This is 0. This is letter O, small letter, and this is the octal digit. Digits can be from 1 up to 7 in base octal, in base 8. Here we see other octal numbers. So this is an octal number, the number in base 8. This is a number in base 8. And all these numbers can be converted to a number in base 10. That means these numbers can be converted to decimal equivalents. Okay, and these numbers has decimal equivalents 1. For this one, decimal equivalent is 16, and for this one, decimal equivalent is 255. So let's practice using the idle shell. So I am typing 0, then small o, then 1. So this is octal number 1. Again 0, o, and 2 0. This is octal number 20. In its decimal equivalent is 16. We can convert 2 0 in base 10 to a decimal number in base 10. I'm sorry, 2 0 in base 8 can be converted to a decimal number in base 10. How do we do the conversion? 2 is multiplied by 8, 0 is multiplied by 8, and we provide powers to the base. So the result here equals 16. In a similar manner, 377 can be converted to its decimal equivalent like this: 3 multiplied by 8, 7 multiplied by 8, plus 7 multiplied by 8, and we put powers to the 8, and the summation result equals 255 here. Okay, so this one can be written like this: 0, O, and 377, its decimal equivalent is 255. In a similar manner, we can define hexadecimal numbers in Python. For this purpose, we use prefix 0x. This is 0, and this is small letter x. Okay, the rest of the digits are in base 10. I'm sorry, are in base 16. So when this hexadecimal number is converted to decimal, what do we get? 1 multiplied by 16 plus 0 multiplied by 16. The result is 16. Okay, 0ff is a very well known hexadecimal number. Here f means 15. If we convert this number to decimal number, I said f is 15. 15 multiplied by our basis here 16. 15 multiplied by 16, this is f, and the second f is multiplied by 16. If we put powers to the 16 and do this calculation, we will get 255. We can also define binary numbers in Python. For this purpose, we use the prefix 0b. So this is 0, this is letter, small letter b. And then we provide a string of 1 and zeros. So this is a number in base 2, or we call it as binary number in short. This is a number in base 2. How do we convert such numbers to their decimal equivalents? For instance, for this one, we have 4 zeros. Our base equals 2. Number is multiplied by the base. We have 4 zeros here. Then we put powers to the base 0, 1, 2, 3, 4. Since the rest of the numbers are multiplied by 0, only this one stays, and that is equal to 16. So the result of the conversion to decimal equals 16. So let's make practice with these numbers. So let me write this one, 0 cross, this is zeros, this is small letter, 1 0, that is 16, 0 x ff, that is 255. I can use small ff, that also gives the same number. Note that Python is case sensitive for variables. I mean, if I type a equals 10 and capital A equals 20, we have case sensitivity here. So small a is different than capital A. But while defining the hexadecimal numbers, we can use capital letters or small letters used for the hexadecimal numbers. They give the same result. Okay, let's continue. Let's inspect this screen. As I just said, this is 255. How do we calculate it in Python? Okay, 15 multiplied by 16 to the power 1 plus 15 multiplied by 16 to the power 0. How can we write it? We can write it using this line. Okay, this part. Power can be taken using 2 stars. Okay, so the conversion of this to decimal can be achieved using these expressions. So the result of both is 255. This is converted to decimal automatically by the interpreter. This is the conversion formula written by us. Okay, this is 2f. Its result in decimal equals 47. How do we convert it to decimal? 2 is multiplied by 16 to the power 1, and f, that is 15, is multiplied by 16 to the power 0, and this calculation can be achieved using this line. Okay, double star means power. Okay, these numbers are converted to decimal. They all are equal to 15. And how do we convert this number to decimal? We multiply it by the base. There are 4 ones. Then we provide powers starting from the rightmost position and proceeding to the left and increasing the power value at each step by 1 to the base, and performing the summation, we get its decimal equivalent. So all these expressions gives us 15. Octal, hexadecimal or binary equivalent of the numbers can also be obtained using octal, hexadecimal and binary prefixes. So this is a conversion method. So let's practice this. If I type octal 64, comma, hexadecimal 64, comma, binary 64, I get equivalent numbers in corresponding bases. Okay, we have here another small examples. We here define decimal, octal, hexadecimal and binary numbers. When they are converted to decimal, they give us the same value, 64. Conversion can be also performed using the integer casting. Okay, here we have decimal number, so the result is decimal. Here we have octal number, base is 8, base information is provided after comma, and the conversion result is 64. This is a number in base 16, this is our base. Automatic conversion is performed, 64 is obtained. This is a number in base 2. After comma we provide the base information. Okay, we can write other bases also, like 3, 4, 5, 6. I mean, these bases are the most commonly used ones, but other bases also can be possible here. And look at here, for these numbers, for instance, for this hexadecimal number, we didn't provide 0x prefix, but it can be provided either also. Here in this one, 0x prefix is provided. For this one also, we didn't write 0b prefix before 1, but it can be provided also. You can omit it or you can keep the prefixes. Conversion will be performed for both cases. So let's try one of them. For instance, let me try this. Okay, this is hexadecimal number. It is converted to decimal. The result is 64. I mean, the same hexadecimal number can be expressed without using its prefix, like this 40, and this is the base. Okay, the result is 64 again. Okay, let me go on with the next slide. Conversion can also be achieved using the eval function. Okay, we just type eval, and these hexadecimal numbers, binary numbers and octal numbers, this is decimal number itself, are converted to their decimal equivalents. Okay, this is another example. We define a hexadecimal number here. This is its decimal equivalent. The same number can be converted to octal using octal prefix, or it can be converted to binary using the binary prefix. Okay, now it's time to see some built-in numeric tools available in the math module. For this purpose, we should import the math module, so we can define pi and e numbers. Let me import the math module. Here. So I mistyped. Okay, now math module is available now. So e math, if I type math e, I see the number e. Of course, pi numbers can also be seen. And here we can use sine function, square root function available in the math module. So what is obtained here? Here we calculate sine 2 pi over 180. This is a number. This is not the degree. Okay, don't confuse it. Inside we have radian, and this is a very numbers very small to very close to 0, so its sign also will be close to 0. And square root can be calculated using the sqrt function of the math module. So square root of 144 and 2 is calculated like this. Power is used to calculate the exponentiation. So this means 2 to the power 4. Double star can also be used for power calculations. This is also 2 to the power 4. But here we have floating point numbers. The result will be floating point. And here we have only integers. The result will be integer. Here also we have only integers. The result will be integer. Absolute value of a number can be calculated using the ABS function. And we have a table here. And the values, the elements of the table can be summed using the sum function. We will see tables in other lectures. We have a table here. Minimum and maximum values of the tables are calculated using min and max functions. Okay, so in the previous screen I provide quick information. Now here let's see them one by one. Square root of 144 is calculated using a sqrt function of the math module. This square root of 144 can also be calculated using double star. So what is the meaning of this? 144 to the power 0.5. This means 144 square root. Or we can employ the power function for the square root calculation. Large numbers can also be calculated using functions of the modules. If we have a large number here, its square root is calculated. The same number can also be used for the square root calculation in this expression. Or we can use the power function here. So let me just practice this. For instance, let me type this. Power 144 0.5. Okay, here we can calculate the square root of 144 using this expression also. Or math function sqrt can be used to calculate the same power. In this lecture, I will explain division, floor, and truncation operations in Python programming. Let's see the division and floor first. Division is performed using the slash symbol here. X/y is the classic true division. It performs classical division and it keeps remainders in the floating point result regardless of the types. If you use double slash like this, in this case we have floor division. This is also called floor division. The previous is classical division. Okay, in this floor division, truncation is performed. Remainder is always floored to the smaller integer. The result depends on the type of the operands. I mean, the result can be an integer or floating point number. We will see the subject better with examples. So this is classical division. The result is 2.5 and this is a floating point number. Here both numbers are integers, but the result is floating point number, fractional number. Here we have an integer and floating point number. The result is 2.5. it is floating point number. So these are classical division operations. We have two division operations here. So the result is 2.5 for both operations. And now consider the floor division. We use double slash here. The result is 2.5, but this is floored to the nearest smaller integer, that is 2. And what about the result? The result is an integer here. Here, one of the arguments here is floating point number. This is integer. The result is again 2, but in this case the result is floating point number 2.0. Okay, if one of the arguments is floating point number, the result is floating point number. But for classical division, the result is always floating point number, irrelevant of the argument types. Okay, now let's see the explicit floor operation. For this purpose, we need to include the floor function. And for this purpose, we first import the math module, and math floor 2.5 results in 2. Math floor minus 2.5 is rounded to the nearest smaller integer, that is minus 3. And truncation function just removes the digits after that. The digits are removed, and that is also removed. Here we have a negative number, minus 2.5 to that, and the digits are removed. So let's make some practice. Okay, I type 10 divided by 4, the result is 2.5. If one of the numbers is floating point number, the result is the same. 10 divided by 4, now I use floor division, the result is 2. It is floored to the nearest integer. If one of the numbers is floating point number, the result is sorry, I used single slash, I should use double slash. If I use floating point number for the first one, the result will be floating point number. It is still floored to the nearest smaller integer, but the result is floating point. If I type 10 slash slash 4.0, the result is again 2.0. Okay, now consider math module here. Okay, let me import the math module. So if I type math floor 2.5, I get 2. Okay, let me try this negative number. Math floor minus 2.5, I get minus 3. So truncation is also very straight. Okay, let me go to the next slide. Here we have mixed examples to compare the results of the different arguments. Here we have 5 divided by 2. This is classical division. The result is 2.5. This is also classical division. The second argument is minus 2. The result is minus 2.5. Here we have floored division. Here both numbers are integers. Both numbers are integers. The result will be integer. For the first division it is 2. For the next division, division result is minus 2.5, but it becomes minus 3. It is floored to the nearest integer. Here let's compare these two. As you see, both are classical divisions. For classical divisions, whether you divide integers or you use floating number for one of them, doesn't matter. The result is always expressed in floating point format. So here only integers are available. Here second number is floating point number, the fractional number, but the results are the same. Now consider float division. Here one of the numbers is floating point number. This is floating point number. In the previous combination, both are the integers. This is integer, this is integer, this is integer, this is integer. Here the results are integer, 2 minus 3. Here the results are floating point numbers, 2.0 minus 3.0. Okay, they have equal magnitude, but the types are different. Okay, let's make some practice here also. Okay, this is new to you. Let's consider this. You already know classical division. And now let's compare it with this one. As you see, we have 2 minus 3, but these are integers. Here we have floating point numbers, 2.0 minus 3.0. Why? Since one of the numbers is of floating point type. For classical division, just keep in your mind that the result is always floating point. If I type 5 divided by 2 or 5 divided by 2.0, does not matter. The result is always floating point number. Okay, let me go to the next slide. Here again I import math module and this is classical division, this is floor division. Now inside truncation function I perform classical division, and truncation just removes the fractional part. Okay, this truncation result is minus 2. In the previous operation we get minus 3. Just to make a comparison, we have seen this example. Okay, now we have division operations. Let's try to compare them and understand the differences between them. Again, we are making a practice here. This is classical division. This is classical division. Classical division, classical division. For classical divisions, the result is a floating point number. For classical division, the result is floating point number. It doesn't matter whether one of the numbers is integer or not. The result is always floating point number. So for this one, the result is 2.5. For this division, although this second one is floating point number, it doesn't make any sense. The result is again 2.5. For the first one, it is also 2.5. Here the second number is negative. Here the result is minus 2.5. Here both numbers are integers, but the result is the same as in the previous one. Okay, now let's compare these divisions. 5 divided by 2. In classical division it is 2.5, but it is float. The smaller nearest integer is selected, that is 2. For this division, classical division result is float to the nearest smaller floating point number. Why? The second argument is here floating point number. So what about this? We have a negative sign here, and this is floating point. The result will be floating point. It is in classical division we get minus 2.5, but this is float to minus 3, and the result is floating point. For this one, the result is minus 3, the result is integer. Okay, now we have mixed type of divisions. This is classical division, result is 3.0. This is also classical division, result is 3.0. This is float division, the result is integer, that is 3. This is float division, the result is 3.0, since this one is floating point number, fractional number in other words. So we can make practice using this. Okay, let me again choose this line, since classical division is very straight. The result is always floating point number. Okay, let me type it again. Okay, let me write it myself. Okay, let me make some practice now. I will use this line. Okay, on the left hand side, let me type the commas. 5/2. The result is 2. 5/2.0. The result is 2.0. That is floating point number. 5/-2.0. The result is -3, and 5/-2. The result is -3. We can write these divisions on the same line, separating them by commas like this. And finally, I have 5 divided by -2. The result now is expressed as a table. Okay, so division of the first, division of the second operation, division result of the third, division result of the last operation. In this lecture, I'll deal with the comparison operators used in Python programming. So, comparison operators return Boolean variables which are true and false. Here, smaller than comparison is performed here, 1 smaller than 2. The result is true. Here on the left hand side, if I type 1 smaller than 2, the result is, as you see, is true. 2.0 greater than or equal to. This is true also. The result is true. As you see, we are using here floating point type number. Here we are using integers. So mixed types can be used with comparison operators. This is equality check. 2.0 equals 2.0. It is true. This is not equal to operator. So 2.0 not equal to 2.0. This is false. So let's make practice. 2.0 not equal to 2.0. So this is false. If I type, for instance, 2 not equal to 3, so this 2 not equal to 4, this is true. And now let's see chain comparisons. A smaller than B smaller than C is equivalent to the Boolean test A smaller than B and B smaller than C. For instance, let's define 3 variables x, y, z having values 2, 4 and 6. This is chain comparison. First, x smaller than y is evaluated, then y is smaller than z is evaluated, and the results are ANDed. If both results are true, the result of the chain comparison is also true. So as I just said, such a writing equals to this one, x smaller than y and y smaller than z. So let's make practice. So x equals, let me use small letters, x equals 2, y equals 4, and z equals 6. If I type x smaller than y smaller than z, what do? I check whether x is smaller than y, then y is smaller than z. If both are true, the result is true. So in this case, both are true, and the result of the chain comparison is true. If we type x smaller than y and y smaller than z, we get the same result. Let's try it on the left hand side. X smaller than y and y smaller than z. Okay, that's also true. Here we have another example. We are using the same values for x, y, z. X equals 2, y equals 4, and z equals 6. X is smaller than y is greater than z. So the first comparison is true, but the second comparison, y greater than z, it is false. And true and false gives us false. So as I just said, such a comparison equals to x smaller than y and y greater than z comparison. Okay, we can use numbers directly for comparison. For instance, 1 smaller than 2, 2 smaller than 3, and 3 dot smaller than 4. The result is true, since all three comparisons produces true, and end of these results is true as well. What about this? 1 greater than 2, this is false. So no need to check the others, since if we get a false result without looking to the others, we can say that the end result is also false. So let's make some practice. So again, using the same values, we can check this comparison. X smaller than y greater than z. So the result is false. Okay, let me try this also. 1 smaller than 2, smaller than 3.0, that is smaller than 4. The result is true. Okay, now let's consider these examples. 1 equal to 2, 2 is smaller than 3. So the first comparison result is evaluated. This is false. The second comparison, 2 is smaller than 3. This is true. And their end is taken. The end is false. And another important thing, floating point numbers may not always work as you would expect. For instance, here in this example, 1.1 plus 2.2 equality check 3.3. This is true, as we know, but the result is false. What is the reason for that? In computer, it is not always to represent fractional numbers by bit strings. Approximate numbers are obtained, but not exact numbers can be obtained for some fractional numbers. This is the reason. So an approximation is performed for this one, an approximation is performed for this one, and the result is close to 3.3, but it is not exactly 3.3. For this reason, the result of this comparison is false. So let's try it. Here, let me copy it and paste it here and press enter. As you see, the result is false. Why? This number is not exactly represented, but an approximate value is available for this number. Similarly, for 2.2, exact representation is not possible, but very close value is available. For instance, let's look at the summation. As you see, the result is 3.3 and some more numbers we have. The result should be 3.3. But as I just explained, fractional numbers may not be exactly represented by bit strings in computer. This is the reason. Such a comparison result is false, but we can say that it is like this for every fractional numbers. Some fractional numbers may be represented exactly. For instance, 2.5 plus 2.5. Let's say that that is equal to 5. I have used a single check, that's why a problem arises. I should use two equality sign. Okay. And the result is true, as you see. These numbers cannot be expressed exactly, but 2.5 can be expressed exactly. So the comparison result here is true. And we have a tricky way for those numbers who cannot be represented exactly. We can truncate, okay, the fractional part using the integer subcasting. Here 1.1 plus 2.2, the result is converted to integer. Here 3.3, the result is converted to integer. So what do we do here? Okay, let me type it here. A truncation is performed. So this is not a very good comparison. In this lecture, I will explain the bitwise operations used in Python programming. Let's study the subject with some examples. Here I define a variable, and 1 is the value of the variable. This is shift left operation. If we convert 1 to binary, that is also 1. If we shift this number to the left by 2 units, that means 2 new zeros are added to the rightmost positions. So we get 1, 0, 0. The leftmost bit is not very important, since all the leftmost bits are zeros. So 1, 0, 0 when converted to decimal has the value 4. And here this is the bitwise OR operation is performed. The value of the x is still 1 here for this example. So we have 1 here. 2 in binary can be represented as 1, 0. If we take the bitwise OR of the bits, what do we get? 0 or 1, we get 1. 1 or 0, we get 1. And this is the binary equivalent of decimal number 3. So the result will be 3. And this is the bitwise AND. Since x is already equal to 1, if we take its bitwise AND bit 1, this is also 1, we get 1. The result is 1. So let's try these examples using the idle shell. X equated to 1. If we shift x to the left by 2 units, we get 4. We can shift it to the left by 3 units. In this case, we will get 8. We can shift by 4 units. We will get 16. Since shifting by 4 units means placing 4 zeros to the right side of 1. And when this is converted to decimal, we get 16. And x bitwise or 2 produces 3, as you see here, and AND operation also produces 1, as we just explained. We can consider other numbers. For instance, x can be 5. 5 means 1 0 1. Okay, in binary, if we shift it to the left by 1 unit, what do we get? We just add 1 0 to the least significant position, and when we convert this number to decimal, what do we get? From this position we get 0 1 2 3 8, and from this position we get 2. If we sum these two, we get 10. So let's shift x to the left by 1 position, and the result is 10. Okay, see the next slide. Here we define a hexadecimal number 0 cross ff. We can convert it to binary using the bin prefix, and in f we have 4 ones in binary. For the second f we have another 4 ones, so in total we have 8 ones here in this string. And this symbol is used to take the bitwise exclusive OR of two binary or two numbers. So binary equivalent of x is all ones. We have 8 ones, and 1 0 1 0 1 0 1 0 is another binary number. If we take the exclusive OR of these two, what do we get? If same bits are used, exclusive OR result is 0. Remember, x exclusive OR y equals x prime y plus y prime x. This plus is of course OR operation. If both are 1, the result will be 0. If both are 0, the result will be 0 also. If one of them is 0, the other is 1, the result will be 1. So 1 0 produces 1, 1 1 produces 0, 1 0 produces 1, so 1 1 produces 0, and 1 0 produces 1, 1 1 produces 0, 1 0 produces 1. So when we convert this number to decimal, we get 85. So let's make practice. Okay, x is defined as 0x ff. We can convert it to binary using bin x. Okay, this is the binary equivalent of ff. We can take the exclusive OR of x and binary number 1 0 1 0 1 0 1 0, and the result is 85, as it's seen here. Okay, consider the next slide. Again, we are considering the same number. Here, exclusive OR of x and binary number 1 0 1 0 1 0 1 0 is taken. The result was, remember, 85. We can convert 85 to binary, writing bin in front of the number. So let's try it. If we write bin here, we will get the binary equivalent of the result. Okay, this is the binary equivalent of 85. 85 can also be expressed in hexadecimal notation. We can convert 85 to hexadecimal numbers. just typing hex in front of the 85, we get hexadecimal equivalent of 85. That is 55. 0 cross 55. Okay, now we see another example. X is 99. We can obtain its binary equivalent using bind x. And another example, 256 is an integer. We can obtain its binary equivalent. Okay, typing bind in front of the digit. And let's consider how many bits are there here. For 99, 2, 6, 5, I'm sorry, 2, 4, 5, 6, 7. We have 7 bits. Here 1, 2, 3, 4, 5, 6, 7, 8, 9 bits. So 9 bits are required to represent 256, and 7 bits are needed to represent 99. Okay, let's try these simple examples. Bind 256, and we get the binary equivalent of 256. Okay, here again x is equated to 99. Bind x gives us the binary number, and here we type x dot bit length. Bit length function calculates the number of bits in the representation of x. So how many bits do we have? 1, 2, 3, 4, 5, 6, 7. We have 7 bits. Okay, 7 is the result. Here binary representation of 256 is obtained, and the bit length function gives the number of bits in this string. How many bits do we have here? 9 bits. Okay, this is the next slide. What is different from the previous one? We use the len function here. X is converted to binary. Len x, len bind x calculates the string length. So this is all the string. So 7 bits are available here, and 2 more characters. In total we have 9 characters here. So the result of this operation is 9. 9 minus 2 gives us 7. Okay, bit length function just counts the number of bits. There are 7 bits here. But len function calculates the length of the string. Okay, string is this one between single quotation marks, and inside this string we have 9 characters. Okay, let's consider the next example. This is the binary equivalent of 256. How many bits do we have here? After the letter B we have 9 bits. What about the length of the string representing 256? Here between single quotation marks we have 11 characters. 11 minus 2 gives us 9. Okay, let's make some practice. Capital X equated to 99, and let's see its binary equivalent first. Okay, this is the binary equivalent, and if we type capital X bit length, it shows the number of bits in the binary representation of the capital X. If we type length bind x, this gives the length of the string including 0 and B, and of course all the bits. And of course if we subtract 2, we get 7. Okay, let me type again. Okay, we get 7.